Hi students, welcome to the next topic from magnetic effect of current, or we also call it as moving charges and magnetism. Today we are going to talk about something called torque. So torque from first year itself we have learning. So how many torque equations we are learning in physics? Have you remember anything something like that from your past experiences? There are 4 torque equations are available in the entire physics. First torque you will learn in work power energy, or you have learnt in work power energy. That is the first torque equation, or that is a fundamental equation. Their torque is equal to force into perpendicular distance between the forces. So you can write introduction to torque as an heading, introduction to torque. So work power energy, you are learning your first torque equation. Torque is equal to force into perpendicular distance between the forces. And the second torque equations you have learned in rotational dynamics, rotational motion or rotational dynamics. Rotational dynamics, after you are learning, torque is equal to I into alpha. I is called the moment of inertia, alpha is called angular acceleration. Third torque you are learning in the chapter of electric charge and electric field. Electric charge and electric field. Here torque is equal to P cross E, or we also call it as PE sin theta without vector notation. And the third torque we are going to learn in this chapter on moving charges and magnetism. So moving charges and magnetism, or this chapter is also called magnetic effect of current. Magnetic effect of current. At the moment I am writing these equations, we are going to learn this one. This is called M cross B. So M is called magnetic moment, which is in short we have written as MP sin theta. Cross product means this one. So in the entire physics, both combining your first year as well as to your second year, 4 torque equations we have learning. Work power energy, torque is equal to force into perpendicular distance. Rotational dynamics, rotational dynamics, torque is equal to I alpha. Electric charge and electric field, torque is equal to P cross E. P is called electric dipole moment into electric field. Moving charges and magnetism or magnetic effect of current, we are learning torque is equal to M cross P, MB sin theta. M is called magnetic moment. Last class we have learned about what is called magnetic moment. Last session in very detailed way. So this is an intro to the torque, and this is what we have learned so far from physics up to maybe up to here. But yeah, just it's a small recap for you. Nothing fundamentally will be there, but just to understand. Okay, keep it in mind. Anyway, definitely this will be come to your mind whenever you are writing some questions, or you are try to solve some questions. So let's move to the more about this properties, magnetic effect of current. Torque is equal to M cross P. Okay, so let's see the detailed analysis of this one. What all the things are involved in magnetism and how we are reaching to that equation. This is the context of the discussions for today. So write on the heading, torque on a current carrying conductor. Torque on a current carrying conductor. Torque on a current carrying conductor placed in a uniform magnetic field. Uniform magnetic field. Force on a current carrying conductor placed in a uniform magnetic field. Uniform magnetic field. Okay. So let's go and analyze what are the things so far we have learned, and based on that learnings we are going to apply the concept whatever we have learned here only. Okay, so let's take a current carrying conductor. So let me have a current carrying conductor like this. This is, suppose for example, carrying the current in this direction, and this is placed in where? Current carrying conductor placed in a uniform means everywhere it is same, uniform magnetic field. So we placed it in a uniform magnetic field like this. Okay, so force torque on a current carrying conductor placed in a uniform magnetic field. So we are placed in a uniform magnetic field, and what will happen? This is, we are assuming as it is a rectangular coil, for example. Look like me a square, right? Okay, so if it is a square, if it's rectangle, no issues. So similarly it's a coil. So let me assume this length is equal to A, and this length is equal to A, and this length is equal to B, and this length is equal to B, for example. And magnetic fields are cross sign, which means that magnetic fields are where? Magnetic fields are into the board. Into the board. It's perpendicular to the board. So what will happen in these cases? This is the direction of current. Whatever I have marked to you is the direction of current. Okay, so here we have to use either there are two options will be there. We need to find out this this conductor which is carrying a current. Listen very clearly, because once this is very clear to you, things are very quite easy. If you are not getting the grip over, he will be here, it will be very difficult. So listen with most accurate way. So this is a current carrying conductor, and this is carrying the current in this direction, and the current is looping here. Magnetic fields are into this one. We have the force equation. F is equal to QVB, or F is equal to I into L cross B. So F is equal to I into L cross B, as this is current, so I will use this equation. Length is in the same direction of current. So this is like L cross. Okay, so L cross B. So here we are going to find out the force L cross B. L is called the length vector. Here length is equal to A. So there is a force, L is in this direction, and magnetic fields are into the board. So I will hold my palm like this, because current or length is in this direction and magnetic fields are into the board. So L cross B, where my thumb will be pointing towards upside direction, and thumb giving a force which is called IAB, because length is equal to A and magnetic field is equal to capital B. Angle between length and magnetic field is how much degree? 90 degree. So IAB sine of 90, will got it. Okay, ILB, L is called this length, L cross B. You have to curl your other four fingers into the board, so you can see your thumb is going upward. So IAB. Okay, so this is one force. This is exactly from the center I will mark. Then we have another force will be here in this direction also. What will happen in this direction? The forces here, current is going downward, so you have to hold your fingers like this. Current is going downward and magnetic fields are into the board, so you have to curl your fingers into the board. So where you can see your thumb is going this direction. So there is a force in this direction, and what is the value of that force will be equal to, tell me what is the value of that force from center? ILB. So F is equal to IBB sine 90. Sine of 90, sine 90, again it's angle between B and magnetic fields into our 90. So F is equal to IBB. Will come here. Here there is a force in this direction. So let's hold my L cross, L is in the direction of current, L cross B, B is inside, so force is downward. What is that force? F is equal to IAB. Here there is a force again, so magnetic field, the L is L cross B inside, so thumb is in this direction, so F is equal to IBB. So you can see there are 4 forces are acting. Okay, this is placed in a perfectly like this. So this IAB force, let me mark this force in a very clear way. Okay, so you can see the coil is not a tilted, coil is in a straight way. That is not tilting the coil is in a straight way and is placed in a magnetic field, and we will experiencing a force F is equal to IAB, F is equal to IAB. Both the forces are equal and in opposite direction they will cancel each other. One reason is they are acting in the same line of action. They are acting in the same line of action. This is equal force IAB, equal force IAB, acting in opposite direction, same line of action. Same line of action means ஒரே line. If you are putting a straight line over here, exactly at the center, it will cancel here. If you put a straight line like this here, this IBB will cancel with IBB. Okay, so we'll write couple of points will be here. F is equal to IAB in upside. Okay, F is equal to IAB in upside, cancel with F is equal to IAB in downside. What are the reasons for this one? The reason is equal force, opposite force, equal force, opposite force, same line of action. Same line of action. If two forces are equal and opposite, same line of action. And same line of action, this will be getting cancelled out each other. What is simply called line of action? Line of action means, suppose you are assuming this is the border of my board. My board is this much length, it will be here from here to here. Okay, I am pulling the board like this, and you are also staying on the other side, and you are also pulling the board like this. So if you are pulling exactly at the center here, and if you are pulling exactly at the center here, what will happen? We are both are pulling with equal forces, means board will not move, board will be there. But I am pulling here in this direction. This corner I am pulling like this, and you pulling this corner. Then the effect may not be the same. Board will have some jerking motion, for example, right? So our line of action has to be same. Then exactly pakka it will cancel. Otherwise we cannot say it is cancel in 100% cases. Okay, so line of action should be on the same line of action, then the forces will get cancelled provided if it is equal. And the same case is applicable. The same case is applicable for when F is equal to IBB in right side. Cancel with, here cancel with F is equal to IBB. F is equal to IBB in right side, cancels with F is equal to IBB in left side. Okay, so both forces will get cancelled. F is equal to IBB in right side cancel with F is equal to IBB in the left side. Both will be getting cancelled. Again the same reasons will be here. What are the forces? These forces are equal forces and opposite direction. Equal forces and opposite direction and same line of action. Same line of action. So because of these 3 points, all the forces will be getting cancelled outside. And what happened to this coil? Nothing will happen. Coil will be in rest. So based on these 2 points, so total there are 4 forces are acting. So 2 with 2, this with this and this with this will be cancelling each other, and coil have no translatory motion. Translatory motion means what? It is not moving to left, it is not moving to right. That is the meaning. It has no translatory motion. It has no translatory motion and no rotational motion and no rotational motion. No translatory motion and no rotational motion, which means it's not rotating, it's not moving. Translatory means either it is moving in x-axis like this, or it is moving in y-axis like this, or it is moving x and y-axis like this. So any motion, it's not at all moving. And another one is it has no turning effects. Rotational motion, it has no turning effects. So no coil have no translatory and no rotational motion. Important. Okay. Because forces itself will be cancel each other. So if there exists a total force, we can say there is a chance for torque, because torque is equal to force into perpendicular distance. All the forces are here cancel each other. There is no force. If there is no force means there is no torque. Forces are cancelling each other. If forces are not cancelling each other, there is a chance that this will have a turning effects. So force will be here and force will be here on same line of action, cancelling, and there is no torque effect for this one. So F net, total force, will be equal to 0. Okay. So this is one area under this one. Now what we are going to study is, the coil is not placed in a symmetrical or in an horizontal way. Coil is going to tilt with a certain angle. So what will happen in that case? That's what we are going to see. Okay. So we'll see. Okay. Now the coil is placed with certain, coil is tilted like this. Coil is tilted like this. This length is called A, this length is called A, and this is B, and this is B. But still, the magnetic fields are into the board, and it is a uniform magnetic field. And it is a uniform magnetic field. Here what will happen? Coil is tilted. Coil is not in a straight way as like what we have shown before. So you can write, if coil is tilted, so initially straight line, you have to assume in a 3-dimensional way. So initially it's a straight line, and now it is little bit of tilted with respect to the horizontal. Okay, so I can say this tilting angle will be equal to theta. Theta degree, it is just rotated. So it is tilted by an amount of theta. By an amount of theta. If a coil is tilted by an amount of theta, what will happen? Same cases will be here, right? Here also we have one force, F is equal to IAB. Here also we have force F is equal to IAB. Here also we have one forces will be here. Okay. So two forces is acting will be here, over here and over here, bottom part and upper part. Both forces are acting over the regions will be here. Either upside forces and downside forces will be here. Okay. What is that upside forces and what is the downside forces? Then there is one force, F is equal to IBB. Here also F is equal to I into length is BB. So what is the point will be here? Here, what is the difference between the previous case and this case? Here, the important thing is like, if the coil is placed exactly, let me take a book up, so I'll show you how exactly it is coming. Okay. I just have one diary book with me. So this is like, initially the coil is placed in a straight way like this. So one force is upside, one force is this side, and one force this side, and one force this side. Coil will not have any translatory motion, not going up, not going left, right, down, x and y axis, and it's not going to rotate. Now the situation is different. The coil is not placed like this one. Coil is placed little bit of angle. Now you can see this white part, right? Now you cannot see the white pages. From your point of view, you can see only this red part. Now if the coil is little bit tilted, now I know you are seeing little bit of this white area because the coil is tilted. Now the forces are acting here. You have to assume one force is acting here in this direction, another force is acting here. Both forces are acting like this. These are these two forces, F is equal to IAB. Then upside, F is equal to IBB one force and F is equal to IBB one force. So these two forces are going upside and going downside are exactly in the same line of action that will cancel each other. But here this is not line of action. If it is here, if it is giving like this and like this, then it will cancel. Now it is tilted like this. So one force like this, another force like this. So what will happen? If somebody is pulling like this one, this book will be supposed to turn. Turning effects will be there because the net force is not cancelling each other. It has some turning effect. See, I am holding, my hand will be here and this side. So both are pulling in this direction, means this will undergo a turning effects. So I can say F is equal to IBB upside cancels with F is equal to IBB downside. F is equal to IBB downside. So there are certain reasons, because it is equal force, opposite direction, same line of action, but F is equal to IAB not cancels. F is equal to IAB. This is like this force. So there are two forces will be there. F is equal to IAB right side not cancel with F is equal to IAB towards left side. The reason is like that. These are equal forces, there is no doubt. These are opposite direction, no doubt. Opposite direction. And no line of action. So this is past, but this is a difference between these 2 points. The third point is a difference, right? The third point is a difference between these two cases. It's not in the line of actions. So because of this one, these forces will not get cancel each other, and it has a turning effects because this is already tilted by an angle of theta. Because of that one is pushing this side, another one is pushing this side. Earlier it is like this. Now it is a little bit like this. So it is not cancelling each other, and there is a turning effect, rotational effects will be there. Okay. So now we will represent this diagram. The same diagram will be representing, we want to derive the torque equations. To derive the torque equations, we are going to do the derivations part. So let me draw these diagrams like this one. So as I told before, we have the coil like this in short. So here we have a force F is equal to IAB. Here we have a force F is equal to IAB. But remember, that is an angle called theta. Because of this one is pushing in this direction or another one is pushing in this direction. It has a rotating effects. Okay. So because of this rotating effect, what will happens? This distance, I mean this distance between the two forces, I have to mark it down. So actually this coil center, okay, if you are taking exactly the center of this coil, you can see Anyway, I know these forces are cancelled. F is equal to IBB, exactly at the center. F is equal to IBB. Now this is a line and its center will be here, and this is a line and its center will be here. So this is a force, F is equal to IAB. This is a force, F is equal to IAB. Force will be acting at the center. That's what the same reason I told. This is not at the line of action. This is the distance. This is the distance between them, and this is called B. So now the same diagram, and this will be makes how much angle? Theta. So let me draw this diagram will be there. So this is one force, F is equal to IAB, and there is another force, F is equal to IAB. Not in the same line of action, right? Because it is tilted. Earlier it is not tilted, means both are in the same line. Now both are not in the same line. If you draw one line like this one, this is called theta, and this is like half. So this is B by 2 and this is B by 2. Now what is called a torque? Torque is the force into perpendicular distance. So this is one force, this is another force, and this is called the perpendicular distance. Perpendicular distance between the forces. Perpendicular distance between the forces. So we are going to see the perpendicular distance between the forces. F is equal to IAB and F is equal to IAB because of these two forces. Okay, so let's see. So we have two forces, F is equal to IAB, F is equal to IAB the left side, and this total distance is B, which is divided into B by 2 and B by 2 as two sections. Now here we have to see what is the total force acting over that area. What is the total force acting over that area? So overall we can say this force will be equal to, okay, this is like B by 2, or all together we can say the total distance is equal to B. If this angle is theta, this is theta, then we can say this is called B cos theta and this is called B sin theta. So torque is equal to force into perpendicular distance between the forces. Perpendicular distance between the forces. What is the force will be here? IAB into perpendicular distance between the forces is called IAB. This is magnetic field, capital B, and this is capital B. Here I have written small letter b, capital B, capital B. Magnetic force, right? Magnetic field is B. B into sine theta. Okay. For a current carrying conductor, okay, see, A into B. A into B. A is this length and B is this length. A into B is called what? Area. So I know A into B is equal to area, which is equal to capital A. So I into A into capital A, then magnetic field B, and then sine theta. We know other equations called magnetic moment equal to current into area. Current into area. So torque is equal to IA is called M B sine theta. So torque is equal to M cross B. This is the equations for torque. This is what I have written in the beginning of this chapter. So this is magnetic moment is equal to IA for one coil for one turn of the coil. One turn of the coil. If there are n number of coils, so you can write it as M is equal to NIA for n turns of coil. For n turns of the coil. For n turns of the coil, M is equal to NIA for n turns of the coil. Torque is equal to M cross B, and which is called MB sine theta. Okay. So, if it is called for n turns, torque is equal to M cross B, which is equal to NIA cross B. Here n is a number of turns, a scalar quantity, current is a scalar quantity, A is the area and B is the B, magnetic field. A is called area vector, B is called magnetic field. So this is the direction of torque. So which means I can say direction of torque decided by vector A and vector B. Okay, this is one point. Second point, theta is the angle between angle between area vector and magnetic field. Area vector and magnetic field. We'll write it as a sentence. And magnetic field. Theta is the angle between area vector and magnetic field. So this is important. Okay. Theta is the angle between area vector and magnetic field. Let me write some stuffs will be here, or I need some more information has to be right. Okay. So the first important point, when the coil is placed parallel to magnetic field, when the coil is placed parallel to magnetic field means I know my magnetic fields are where? My magnetic fields are into the board. So into the board means I am placing my coil in the direction of magnetic field. If I am placing my coil in the direction of magnetic field, because this is the direction of magnetic field, my area vector is like this. So this is the plane area for me. This is a plane area and the area vector is out here and it's out here. So the angle between, when the coil is placed parallel ke 0 nu use koodadu. Okay, that is a misunderstanding will be there when you see parallel theta equal to 0. No, it's not like that. Whenever the coil is placed parallel to the magnetic field, area vector is perpendicular to the surface. So the angle between area vector and magnetic fields are going inside the board. This is called area vector. So in that cases, angle between area vector and magnetic field is how much? 90 degree. When coil is placed parallel to magnetic field, angle between area vector A and B is 90 degree. So torque is equal to MB sin theta. So torque maximum torque you will get, and that torque is called torque is equal to MB because theta equal to 90 degree. Second point, when coil is placed perpendicular to magnetic field. Coil is placed perpendicular to magnetic field. When a coil is placed perpendicular, so I know magnetic fields are into the board. If you are keeping like this, then it is parallel. Now perpendicular means you have to keep like this one. If you keep like this one perpendicular, then magnetic fields are into the board and this side area vector is also into the board. If area vector is into the board like this, correct? Area vector is perpendicular to the surface. So in this side area vector is into the board. Magnetic fields are into the board. So angle between, then I will say angle between vector A and vector B is equal to 0 degree. Torque is equal to MB sin 0. Torque is minimum, which is equal to 0. So torque may be maximum, torque may be 0 and 90 in two different cases. When a coil is placed parallel to magnetic field, means area vector is perpendicular to my parallel theta equal to 0 nu substitute pannakoodadhu. Inde logic theriyana. Logic is important. Based on the logic only this is saying. When you see the word called parallel, immediately go and substitute theta equal to 0 degree. It's wrong. It's not correct way. Okay. When a coil is placed parallel to magnetic field means the angle between the parallel means coil is like this. So this is the area vector. Magnetic fields are into the board. So both are making 90 degree. So 90 degree will substitute. When a coil is placed perpendicular means like this. So area vector is here. In this side area vector is here. This side area vector will be here. So if you are taking this area vector, then sine area vector is outside, magnetic fields are inside. Both are opposite, which means angle between them is 180 degree. But if you take this surface, you have two surfaces, right? This surface and this surface. If you are taking this surface, then area vector is outside like this. So area vector is into the board. Magnetic fields are into the board. Both are 0 degree. Then torque is equal to 0. If you are taking this surface, then area vector is always outside the surface and perpendicular to the surface. So area vector is towards you. And magnetic fields are towards the board. Both are making 180 degree. So sine of 180 is again 0. So torque is minimum. But if you are taking this surface, theta will be equal to 0 degree. So remember, when a coil is placed perpendicular to the magnetic field, theta equal to 0 or theta equal to 180 is possible. Whenever a coil is placed parallel to magnetic field, theta will be equal to 90 degree always. Hope the torque sessions from moving charges and magnetism is clear to you. Okay.